Agree? Okay? So that goes the definition of basis. A basis must be able to represent every point, right, in the space that it's supposed to represent. Alright? Okay? Now, the second question is, if I have two vectors like that, right? This is still 1, 0, but this is maybe 1, 1 or something. Can it still represent, can these two vectors still be the basis vectors to represent the entire plane? Can or cannot? Can, right? Right? Right, but we tend to, but usually we don't want that. We want to avoid that for a very simple reason. For a very simple reason. I try to explain without using the pen and paper, but if there's a problem, I'll use pen and paper. Now, for this case, when the two basis vectors are orthogonal to each other, that means 90 degrees to each other, right? 90 degrees to each other. Okay? So this is 1, 0, this is 0, 1, right? Yeah? When they are 90 degrees to each other, and you are given a point here, and you want to get the coordinate of this point on this axis and on this axis, it is just a simple process of using this vector dot product with 1, 0 here, right? Yes? And dot product using this vector dot product with 0, 1 here, right? You all know what is a dot product, right? Right? Okay? So it is that simple, right? But and so when you have a orthogonal vector, right? It is easy to know how much component of x and how much component of y is in your vector, understand? Right? Because x and y has got nothing to do with each other. They are orthogonal. Orthogonal means 90 degrees. Right? They don't contain each other. They are just orthogonal, nothing to do with each other. Right? So if you want to know what is the coordinate here, you just dot product with this. What is the coordinate here, you just dot product with this. You don't have to care about the other. Okay? Now when you have two axes like that, then it's a little bit complicated. Because this guy also has a component here, right? And this guy also has a component here, right? So if I have a point here, I want to find what is the coordinate here and things like that. It is not so straightforward now, because if you want to see how much of 1, 0 component here, you have to consider this guy also, right? Yes? You want to say how much of 0, 1 component, the 0, 1 component, both have, this one doesn't have 0, 1 component, this one has a 0, 1 component, right? So for that reason, even though this can be a basis function, we want it to be 90 degrees, right? It's for convenience. Right? For convenience. So basis function is important, and basis function must represent all points in the space that it's supposed to represent. And the other thing is that we want them to be orthogonal, because orthogonal makes it very easy. Right? In finding out how many components are here, how many components are here, right? Now, so if you have three-dimensional same thing, x, y, and z, right? X, y, and z, okay? Now, you want them to be orthogonal also, for the same reasons I mentioned, right? But if they are not orthogonal, can they represent the 3D space? They can, right? But it's not so ideal. Okay? Okay? Now, at this point in time, I digress a little bit. Because that's what will help you see some intuition of the mathematics. Now, for the two-dimensional case, right? This vector, what is the dimension of this vector? 2 by 1, right? Right? This is 2 by 1 also, right? When you put them together, 2 by 1 and 2 by 1 vector, you get a 2 by 2 matrix, right? Yes? Yes? 2 by 2 matrix, okay? Now this is, again, I digress a little bit, but just to help you see something. tells you a lot about the orientation of this vector. Alright, the component vector, right, in the matrix. It tells you about the orientation of this vector. Alright, for example, if the two vectors are like that, can they represent the 2D plane? Cannot, right? Because it cannot, no matter how you add or minus the two components, you're going to represent only a line, like one dimensional, right? Same thing, if you're like that, it's also one dimensional, right? Right? It's only like that, and you can do two dimensional, right? Right? Like that also can do two dimensional, right? Now, what happens if mathematically they are aligned, right? If I lift up a little bit, can it represent two-dimensional plane? Right? You can, right? But you want to avoid these cases because it could well be noise, when you measure the data, things like that, right? So you want to have a measure of whether is it like that or like that, right? Yes? Right? And the measure is something that you all must have come across in your high school, secondary school. Alright? And the measure is something called, anyone? Anyone? It's called the determinant, understand? The matrix, right? You have two vectors, you put them into a 2 by 2 matrix. If they are like that, your determinant is 0, understand? If you're like that, the determinant is 0. If you're like that, the determinant is big. If you're like that, the determinant is bigger than 0, but quite close to 0, understand? Yeah? Yeah? So, when you do math, right, when you do your linear algebra, if you want to invert the matrix, you look at the determinant, right? If the determinant is 0, can you invert? You cannot, right? So there are physical meanings to this. Okay? Now, three-dimensional, same thing. For three-dimensional case, right? What is the dimension of my vector? 3 by 1, right? Three numbers. And if I have three numbers add up and you arrange them in the matrix, it's a 3 by 3 matrix, right? Right? Now in the 3 by 3 matrix, you also can find the determinant, right? Any matrix you can find the determinant, right? It's the same thing. Now in the 3 by 3 matrix, all the vectors are like that. What's the dimension it can represent? 1, right? 1 also, right? 1 also, right? Because no matter how you add or minus the 3 axes, you are going to lie on the same line. So it's one dimensional. If the 3 axes are like that, or like that, then it can represent all points on this plane, but not the depth, right? So it's 2-dimensional, right? Okay? Now, when it is like that, then it's 3-dimensional, isn't it? Okay? Okay? Similarly, if it is like that, can it represent 3 dimensions? Yes. Right? But it's not good. Right? Because this could be just noise, right? When you get data and things like that, it could be just noise, right? Right? It's not so good. And similarly, in a 3-dimensional world, it's the same thing. If you put them into a 3 by 3 matrix like that, right? If you compute the determinant, it's going to tell you something. If the determinant is 0, means they are on the line. If the determinant is not 0, big number, that means it occupies the 3-dimensional space, understand? If the determinant is 0, it could represent, 0. If the determinant is 0 for 3-dimensional case, it could represent a line, could represent a plane also. It's just not full space, understand? Okay? Now the 3 by 3 matrix, right? If you compute the determinant, actually you're computing the parallelogram, the volume covered by these vectors, understand? So the biggest volume happens when you have orthogonal to each other, okay? Okay, so that's a digression to help you visualize a little bit the kind of linear algebra matrix and vectors, the kind of things, measures that you have been using and what it actually means. In this class, I want you to feel the math, understand? I don't want you to compute too much. So a lot of time I'll just say, is this 0 or is this a big number or small number? I don't actually care, is it 100 or 200, I don't care. Huh? Is it a big number or small number? Because a lot of time, it is the relative strength that matters most. Understand? Understand? A lot of time, it is not how loud I speak. The speech, how long I speak, how long I speak does not define my speech. Understand? Right? It is something else that defines the speech, which is the frequency that we're going to learn. Understand? It's just like in a piece of music, right? Whether you turn on the volume or turn down the volume, it's still the same piece of music, right? So loudness is not what we are after. It is the frequency content that we are after. Understand? Okay? Now, again, I try to do this as much as possible without using the paper, but if I although then I use the paper. So I use this to explain. Now, if you have a vector, if you have a piece of music, right? And a piece of music, the time axis is t, right? Yes? Right? And the reason we hear the music is because of vibration in the air, right? Okay? Now the amplitude of the vibration of the air, right, through time, give us the notion of the audio signal that we're hearing, right? Whether it is speech or music or any type of sound, correct? Yeah? But as I mentioned just now, whether I loud or soft doesn't matter, right? Okay? Now, if you represent that audio signal, right, and you discretize the time, when you discretize the time means this audio signal is a continuous time axis, right? Continuous time. But if you discretize the time and then you put them into an array is a vector, right? A vector, right? And then you put the amplitude value, right? On the array, right? Yes? Are you following so far? I'm doing all these things without writing. If I can get away with this, I'll do it. But you have to write down, right? So if you cannot follow, let me know. Okay, I'll change another way of explaining. So if you plot the values in the vector, it's going to be amplitude of the sound, right? Yes? Yes? Amplitude of the sound, right? Now, let's say if I, every 1 millisecond, you see the time axis is continuous, right? The people at the back, can you hear me? Time axis is continuous. Now, thank you. And if I sample the time in 1 millisecond interval, if I sample the time in 1 millisecond interval in 1 second, how many sampling points are there? How many? 1,000 points, right? Your 1,000 points. So your vector is 1,000 dimension, right? Okay? So we are going to, from now onwards, we are going to deal with vectors of vectors that are very, very long, understand? Okay? But all that I showed you just now still apply, understand? Right? If you want to understand very high dimensional things, our wisdom cannot let us think so big dimension, right? High dimension. But always bring down to 2 or 3 dimensions. Okay? And then understand the problems there. And then you can extrapolate to higher dimension, understand? Right? So, even though we are dealing with a vector of thousands by 1 dimension, right? Many, many points, right? We are going to understand how to deal with these signals by considering 2-dimensional or even 3-dimensional vectors, understand? Considering vectors of much smaller dimension. Okay? Now, again, these are 2 vectors that represent 2-dimension points, right? So this is 1, 0, this is 0, 1, right? And this is a good way to represent all points in two-dimensional world because these two axes can represent all the points and these two axes are 90 degrees to each other there, right? Okay? Now, let me ask you a question. If I rotate it this way, is this still a good basis function, yes or no? Yes, very much so, because it represents all the points and they are 90 degrees to each other, understand? But just now when I'm here, it is 1, 0, right? And when I'm here, it's 0, 1, right? If I rotate it this way, are they still 1, 0 and 0, 1? No, right? The numbers are all messed up already. But it's still 2 by 1 vector. It's just that the numbers are not so nice, not 0, 1 and not 0 and 1, right? It's got some numbers that are non-0 and non-1, right? Yes? Okay? Okay? But the mathematics is still the same, right? Any points here you want to find in terms of this axis, you just dot product with this and dot product with this, right? Yes or no? Okay? Now, sometimes you don't always want to use 1, 0 and 0, 1 Cartesian coordinate. Okay? Okay? To represent some quantities, you want to rotate your axis in such a way that that axis actually represents the kind of things that you are looking for, understand? Because here it's like you want position, so x and y position. Very convenient, right? If you rotate this way, although the numbers are not so nice, not 0 and 1, all messed up, right? But it may these two axes may represent the kind of quantity that you want to represent, understand or not? Yes? Now this is two-dimensional, and for three-dimensional, same thing, right? Right? 1, 0, 0, 0, 1, 0, 0, 0, 1. You can also rotate them, right? And then, but three-dimensional axis, your vectors is 3 by 1, right? And what did I say just now about our audio signal? It's 1000 by 1, right? So you imagine your this one I cannot imagine because we can only see 3D. That 1000 axis, I may need this help now. So you see, for 2D, right, two-dimensional case, your vector is like that, right? So x and y vector, you have 1, 0, 0, 1, right? For three-dimensional case, you have this. Right? Yes? Now for 1000 dimensional case, right? 1000 dimensions. 1000 dimensions, how many vectors, basic vectors are there? How many? 1000, right? So you have 1000 of them. You have 1000 of them. So it could well be 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, etc. until 0, 0, 1, right? Yes? Can this be good? Can this be good basis vectors? Of course it can be good basis vector, right? 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 Okay? But this is only good if you are, say, interested about the loudness of my voice. Right? But we are not interested in the loudness of my voice. We're interested in something else. Okay? Now, 200 years ago, or more than 200 years ago, there's a French mathematician called Fourier, right? Fourier told us that if you want to represent audio signals, right, you should just use sine and cosine, okay? And you know, it's always the case that great mathematician, great thinker tell us something, then when you understand, you think it's very easy, right? But it's not easy to come up with that, right? So now you think about it, right? You think about it, it makes sense. Because it makes sense because Fourier told us, right? So Fourier told us that you need to measure something, say signal, right? in terms of sine waves and cosine waves. Okay? Now, sine waves, as we said, we seen last week, was like that, right? Sine wave, right? Right? And then if I have this kind of sine wave, it means higher frequency, right? Yes? Higher frequency. So there's a notion of frequency, right? And what is great about what Fourier said is any signal, not just audio. So for time being we just say audio. This audio signal, any signal can be represented as a summation of sine and cosine waves, understand? That means you give me all sine waves and cosine waves available, and you tell me you want to form any kind of sound. I will be able to say, I take out from my two boxes all the sine and cosine waves of different frequencies, right? Combine them together and give you the sound that you need. Understand? Yes? So any signal can be decomposed into sine waves and cosine waves. Okay, that's a very useful insight that Fourier told us, right? So in other words, this type of representation may not suit our purpose, right? Right? We want to rotate our axis in such a way that, let's say the axis, okay, I cannot represent 1000 dimension data vectors, right? So I'm going to use 3 dimensions. Or just use 2 dimensional vector, right? Now, how is 3 dimension? 3-dimensional vector, right? But in actual case, in what is happening is you have 1000 vectors of this, right, orthogonal to each other. It's kind of difficult to represent using a 3D or but that's fine, right? So you want to rotate in such a way that all the axes become sine and cosine, understand? You know what I'm saying? You see, just now on 10 and 01, I rotate it, it's no longer 1001, it's some numbers, right? Right? But you want to rotate them in such a way that all the 1000 vectors represent sine and cosine, understand? Right? Represent sine and cosine of different frequencies. Okay? I say again, you have 1000 basis vectors. You know that if you want to represent the audio signals, this is not good. This is not good because it doesn't capture the property that you want to capture. And the property that we want to capture is frequency, right? Right? So instead, you should rotate all the vectors in such a way that this one becomes a sine wave of this frequency, the next one is sine wave of higher frequency, sine of even higher frequency, followed by cosine of this frequency, cosine of higher frequency, etc., etc. Understand? That means you can rotate them in such a way that all the axes become sine and cosine, okay? 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 And you know that they are still orthogonal, right? Okay? So now, if I ask you a question, if I give you an audio clip, right? And I ask you, so audio clip is 1000 by 1 vector, right? And if I ask you, how many 1 Hz signal is there? Right? So what should you do? You see, when it's a 2-dimensional case, right? If I have a point here, I say how many X components are there? What you do is, you take this vector, dot product with 10, right? Dot product with this, right? You take this vector, dot product with this, right? Yes? Now, if it's an audio case, let's say it's a 1000 dimension vector. An audio vector 1000 dimension, right? And if I ask you, how many 1 Hz signal is in this audio signal? What should you do? Very good. What's your name? Stephen, Stephen, very good. So Stephen gave a very good answer. You just need to dot product with the basis vector, then for one that represents 1 Hz signal, right? Right? And why you don't need to dot product with the other one hertz signal, other signals for different frequencies. Why you don't need to do that? Why? Because they're orthogonal, right? You dot product also no use, it's 0, right? Do you understand? Do you understand? Okay? So if I give you an audio signal, I want to find out how many 1 hertz are there. I dot product 1 hertz, and I can go dot product others. I'll get 0 anyway, right? Right? But Stefan's answer was extremely good, but not complete yet, because in fact, it's complete. It's just not detailed enough. There are sine and cosine inside, right? Right? So which one must you dot product with? Both. You must dot product with both, understand? Okay? So far so good. Who don't understand? If you're too shy, okay.
How is the basis vector can be a sine and a cosine? What does that mean?
Oh. If you have 1,000 numbers here, right? Right? 1,000 items here, right? And they are all numbers, right? The numbers can be positive or negative, right? If the number is like 1 represents this shape. If you plot you plot this number out, it can represent sine wave or cosine wave, right?
So that's what you mean by having the basis vector be a sine and cosine.
Yes. Yes. That means you rotate your basis vectors instead of 1, 0, 0, 0, 0, 1, 0, 0. Rotate them in such a way that the values represent sine waves and cosine waves. Understand?
That's possible.
What?
That's possible.
That is possible, yes. That is possible. We will see why that is possible. I mean, not a direct proof, but we will see some evidence. Right? Is it okay? Is it okay? Right, now. Coming back to the sine and cosine thing, right? So Stefan says you need to dot product with signals of 1 hertz, right? Right? And then earlier on, I want the 1,000 basis functions to represent sine and cosine. Right? Okay? I think it's too much to ask this question, but can anyone tell me why I need sine and cosine? Why can't just use sine? Why can't just use cosine?
Different phase.
Different phase. Very good. Your name is? Samuel. Different phase. Very good. Because as it turns out, remember something. All the basis functions must be orthogonal to each other, right? Yes? Right? And then later on, this one you can use math to prove it in your slide. In the note. That if you use sine wave, right? Sine wave of different frequencies, they are orthogonal to each other, understand? That means if this vector represents sine waves of 1 hertz, and then another vector represents sine waves of 2 hertz, when you dot product them, how do you do dot product? You multiply point-wise and sum them up, right? Yes? Yes? So if it's sine wave of 1 hertz and sine wave of 2 hertz, you dot product them, multiply and sum them, you get 0, understand? Because 1 hertz and 2 hertz are orthogonal to each other, understand? Okay? They will only be non-orthogonal if it's like 1 hertz multiplied with 1 hertz, dot product with 1 hertz, understand? Okay? So 1 hertz with 2 hertz, 0. 1 hertz with 3 hertz, 0. Kind of thing. I've explained this with some conditions that I don't want to confuse you. Right? You just take it this way first. Now, since there are sine waves and cosine waves, right? Sine of 1 hertz and cosine of 1 hertz are there, right? Right? And I said that all the basis vectors must be orthogonal to each other, right? 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 The good news is, if you put the sine 1 hertz and the cosine 1 hertz and dot product, you still get 0, right? Sine and cosine are always orthogonal to each other. Understand? Are you following? Yeah? Now. Now, imagine my audio signal. My audio signal is 5 Hz. Okay? It's a 5 Hz sine wave, understand? And then I say I want to find out. So I don't know, I create the 5 Hz signal, I don't tell you, I say, find out what are the frequencies in this signal that I give you, right? So what do? You take this signal, you dot product with all the basis functions, right? Right? So when your sine Hz, your sine of 5 Hz, dot product with sine of 1 Hz, what do you get? 0. When you dot product with sine of 2 Hz, what do you get? 3 Hz, 4 Hz, 5 Hz, not necessarily one. Right? As I say, some big number. I just want you to go some big number, understand? Not 0. Okay? Then 6 Hz, 0, right? And then if you dot product with cosine 1 Hz, what do you get? 0. 2 Hz, 3 Hz, 4 Hz, 5 Hz, 1, right? 1, right? Yes? Wrong, huh? I just told you sine and cosine of orthogonal, understand? So if your signal is sine 5 Hz, you dot product with cosine 5 Hz, you get 0, understand? Okay? So that means of the 1000 basis functions, of the 1000 basis functions, only one vector can give you non-zero output, understand? Yes? Yes? No, I'm explaining by just moving my hand like that. If you understand well, that's the best. But if you don't understand well, you have to let me know, because then I have to change to table format. But it's important that you follow, understand? Otherwise, you'll be wasting your time listening to me. Alright? Yes? Draw out what? Okay. So it's like instead of 1, 0 something, right? You have maybe you have a 1, 0.9, 0.8, 0.85, and then you have minus values until you have 1 here. So this is like a cosine wave, understand? That's what I meant. Understand? So all these values represent the ups and downs. Okay? So that's what I meant by a vector representing sine and cosine, understand? So representing sine, cosine of this, and higher frequency will be like that. Okay? That means the y values, if you plot x and y, the y values are in this vector, understand? Okay? Okay? Now, so if I have a signal that is sine of 1 Hz, I don't tell you what is it. I say, Ivan is our TA, right? Ivan, what are the frequencies inside this signal that I just give you? What Ivan should do is just to take that vector, right? Just dot product each one of them, and then you realize that only one of the vectors can give you non-zero product, dot product, which is the sine 5 Hz. Then Ivan will be very confidently, you tell me that the signal has got one frequency only, which is sine of 5 Hz, right? Yes? Okay? Okay? Now, if I give you a cosine of 5 Hz, I give it to you and say, tell me what is the frequency, what is the signal inside this audio signal that I just gave you. So you can dot product. Which of the dot product will give you non-zero? Which one? How many say sine 5 Hz? How many say cosine 5 Hz? Oh dear. The rest don't understand, is it? How many say cosine 5 Hz to give you non-zero output? it's good that you tell me whether you understand or you don't understand, because then I have to, if I find that most people don't understand, I'll repeat in another form. So in order not to waste time, you have to tell me whether you understand or not. How many say cosine 5 hertz will give you non-zero output? Okay. So that gives us one problem, right? Sine and cosine actually have the same type of signal, right? It's just shifted from each other only, right? Yes? It's just shifted from each other only, shifted by 90 degrees, right? Right? Now, if you have a piece of music, right? And then when you hit my ear, it vibrates in sine form, right? And if I move here, it becomes a cosine form. Does it matter? Does it mean I cannot get the music? No, right? Right? So my ear must be able to process both sine and cosine, right? And in practice, you can never control where the ear is, right? It could be sine, get the sine here, and then you get the cosine here. It could be somewhere in between, right? Right? So you want to capture both. Okay? You want to capture both. Now, listen very carefully, yeah? Listen very carefully. If you have a signal that is pure sine wave, right? And then you go and dot product with the basis function, pure sine wave of that frequency will come out. Let's say 10 hertz will come out, right? Right? And with zero throughout, right? Right? Now, if you have a cosine wave of 10 hertz, right? Only cosine will come out, right? Cosine 10 hertz will come out, right? Now, this is where engineering sense comes in. If I have sine of 10 hertz, right? My signal is sine of 10 hertz. I dot product with a basis function. I get a big value, right? Right? If I move a little bit away, that means this sine is not really sine now. It's more sine. It's still largely quite sine, but a bit of cosine now, right? Right? Because if you move by 90 degrees, it becomes cosine, right? So it moves a little bit only. Yeah? Yeah? Engineering sense tells you that it cannot straight away, the multiplication with sine cannot straight go to zero, right? Cannot, right? Right? There must be some component of this. That means, let's say again, if my sine wave is 5 hertz, okay? I multiply with the basis function with the sine of 5 hertz, right? I get a big value, correct? Now if I shift a little bit, my input shift a little bit, and I still multiply with the same sine of 5 hertz, right? Right? It won't drop to zero. It will drop a little bit, right? Right? And then in the meantime, if I dot product with cosine of 5 hertz, do I get zero now? Yes or no? I get a little bit of cosine component now, right? Yes? Yes? I move more, sine drop, cosine go up, right? I move more like that until I move to become cosine, then sine drop to zero, cosine move to a high value, right? Yes or no? So in other words, Sam was the one who talked about phase, right? In other words, phase is how much you shift, right? It's a shifting, it's a phase, right? In other words, if I want to know, if I give you a 5 hertz signal, for example, I don't tell you it's 5 hertz signal, I just give you a signal, I know it's 5 hertz. And I give it to you. And you can dot product with all the basis functions, right? Right? Then you find that only the basis vector that represents the sine of 5 hertz has got big value, the rest all zero. What can you conclude about the input signal that I just give you? It is a sine of 5 hertz, right? Now, if I give you the signal and then you can dot product, you get only the cosine 5 hertz to give you some value, right? The rest give you zero. What can you conclude about the signal? The signal is a cosine function, right? If I give you a signal and you can dot product, and only the 5 Hertz basis functions will come out. Sine gives you some number, right? That is this number. Cosine gives you some, cosine 5 Hertz gives you this number, okay? What can you say about the signal that I give you? It is a 5 Hertz signal, it's more to cosine than sine, right? And the relative strength tells you how much shift is it, right? Right? Like that is more sine, like that is more cosine, right? In other words, when you have sine and cosine as a basis function, and when you get dot product with them, you by comparing for the same Hertz, right? So 5 Hertz, you compare sine and cosine, right? You know that. You know whether sine and cosine is present there. Okay? And then you also know what's the shift of this signal, okay? Is it more towards sine, more towards cosine, okay? By looking at the relative strength. Do you understand? Yes? Yes?
So must your basis functions always have the same frequency?
Sorry?
Must your basis functions always have the same frequency?
No need. No need. Right. That's why there are some assumptions that if I just say like that, just some whatever I say, it's actually not correct. There are some assumptions that I will told you. Okay? We'll come to that. Right? So the question was, must the basis functions be always 1, 2, or 3 Hertz? No. Right? In fact, the symphony orchestra question, example that I showed you, the basis function, the Hertz is like 0 point something, right? You have a question behind?
Yeah, so since the sine and the cosine part of a signal only depends on your position, is there some way to turn like every signal into a pure sine signal or a pure cosine signal?
The question is, can you turn, it's a very good question actually. If I give you an audio signal, there are sine and cosine of different frequency and different shift, right, for each of the frequency, right? So the question is there a way to shift, turn them all to sine and all to cosine, right? That was the question.
Yeah.
The answer is mathematically you can do that, but in practice you don't do that at all because it doesn't bring you any benefit, right? Now listen, it is the presence of the frequencies and the shift that determine what we hear, understand? If you give me the same set of frequencies and you shift differently, you hear completely different sounds. Understand? So if you want to capture the sound, there's no reason why you want to put them all to sine and cosine. Understand?
Yeah.
Okay, good. So you understand, so there is one more thing that I want you to understand. You know, when you dot product, right? When you dot product, this is 1, 0, 0, 1, right? If I have a vector that is 5, 4, right? 5, 4 dot product with this is 5 and 4, right? Right? Okay? When you have a vector that is 500 and 400, dot product becomes 500 and 400, right? Okay? That means when you do this dot product signal with the basis functions, right? Your result, the magnitude of the result is highly dependent on the loudness, right? Right? On the loudness, because if your signal values are all very big, it's very loud, right? Right? But we know that loudness does not matter. Loudness does not matter. Loudness does not matter, right? Right? Loudness does not matter. It is the relative loudness of the frequency that defines what you hear, understand? Okay? So in other words, even though the input data can be very loud, very big numbers, it doesn't matter because that factor that multiplies the thing, right, applies equally to all the frequencies, understand? So most of the time, when you do frequency analysis, we don't even care what is the absolute number. What we care most is this hertz and this number of hertz, what is the relative strength, and what is the shift, understand? Is that okay? Is that okay? If you really understand what I have been saying for the past 47 minutes or so, you actually are very close to understanding Fourier transform already, Fourier series, Fourier analysis, understand? Because that's exactly what Fourier taught us. Okay? Any question? Yes?
So for you said that we're not interested in the absolute loudness,
Yes.
but which is the relative loudness. So is
Yeah.
there like a function to normalize the loudness if there's any?
So it's another very good question. So the question is, since the absolute value of the vector doesn't matter, I mean the scale of the vector, the number doesn't matter, right? I mean how big the number or small it doesn't matter. It's only, and is there a need to do the scaling, right? In real life, you do, and let's say if you are doing engineering problem, a circuit or whatever, you don't need to take care of all these numbers, all this amplitude, because you don't want them to saturate, right? But in terms of mathematics, you don't care. In terms of mathematics, you just compute it. Okay? Okay, now, for that reason, a lot of time, because the whole thing about all this is not about voting about, I want to teach you in such a way that you can really understand the concept, the core concept. And the core concept, what I require of you is it a big number or small number? That's all I understand. Is it 100 or 200? Sometimes, even if you use the wrong factor, it doesn't matter. In fact, you don't care. Throughout my career, when I do Fourier analysis, there's not even a single time that I need to worry about the absolute value. Okay? It's called the relative value of the for the same reason I told you, right? Loudness does not matter. Okay? Whether you do speech recognition or you do music analysis or whatnot, anything, right? So, is there any question? If not, if you really understand, then later on when we go through the slides, we can go through a bit faster. Okay? Now, I'm going to hand out the first assignment today. Right? I'll give you 1 week to do the assignment. You need to submit it on Canvas. Right? And then the tutorial class will start next week. All of you have no problem signing up for your tutorial class, right? Okay. So, why don't we do this way? Since this is 10:50 now, we take a 5-minute break, we come back at 10:55, and then we go through the slides. Okay? Thank you. is maybe it's a different way of looking at it, right? So hopefully by going through this, you understand it better, right? So basis function, and we all know that circular functions create the sine and cosine, right? So it's something physical. Now, for this thing, what I want to highlight is when you want to represent a sine and a cosine using a mathematical form, you usually write it as sine 2 pi s t, right? Right? F is the frequency, how fast is up and down, right? T is the time, right? So when you want to put it on in the array form, right? Just now I say every 1 millisecond you do it, right? So delta T is 1 millisecond, right? 1 millisecond interval, then you see the sine and cosine, right? So you represent it in this form in your this is the form in your vector, right? In your array, in a computer language array, right? And AK and BK are the strength of that signal, right? Right? Okay? Now, just now, I only use sine and cosine. Now, if I have a signal that's more complicated, I have 5 sine, magnitude 5 of sine 3 hertz plus magnitude 2 of cosine 4 hertz. Okay? Okay? And then I don't tell you, and then I give it to you, right? So rather than write down. Because even I also forget after a while. Then write down. So it's a signal, y of t is 5 times sine of 3 hertz, right? Plus 2 times cosine of 4 hertz. Oh, sorry. Right? Right? This is sine of 3 hertz and cosine of 4 hertz with different strength, right? Yes? Okay? Now, of course, I don't tell you what are they. I just tell you, I have a signal, I just give you the y. I don't tell you the y comprises these two, understand? I just give you the y. And what do? You go to your 1000 basis functions and dot product each one of them, right? Right? And then can you tell me what are the two vectors that will respond with non-zero after dot product? Sine 3 hertz and cosine 4 hertz, right? And the number that you get for sine 3 hertz, is it bigger than the number that you get for cosine 2 hertz or cosine 4 hertz? Yes, right? Right? And the number will be, it won't be 5 and 2, it could be 50 and 20, 500 and 200, that kind of thing. You know what I'm saying? But it doesn't matter, it's a relative strength. Okay? Okay? Yes? That's a very good question. The question is, what if there's a sound wave of 3.5 hertz? Right? Right? No. I simplify things when I discuss, when I give you the example. I say 1 hertz, 2 hertz, 3 hertz. In real life, signals are not 1 hertz, 2 hertz, 3 hertz. It's 3.5 or 3. You have a lot of things. So listen, listen. It doesn't affect anything that we discuss, right? You can have a basis function. You know, I show you the symphony orchestra music, right? That one is 540,000, right? 540,000 frequencies squeezed into the 20,000 hertz, understand? Right? So 500, so 20,000 hertz divided by 540. Can someone compute and tell me? So the each of the step of the frequency is actually 0.0 something, no? Right? But the theory is still the same, understand? You're all talking about, understand? Okay? Okay? But for convenience, I use the 1 hertz, 2 hertz. In fact, human being can't even hear 1 hertz, 2 hertz. What is the minimum frequency that human being can hear? What's the minimum? About 10 hertz. Right? What's the highest? 20,000. elephants can hear lower frequency than us, right? You know, right? Right? So it doesn't matter. It doesn't matter. But it's a very good question. It doesn't matter, right? Now, coming back to this. Coming back to this. So the delta t was the 1 millisecond that we used just now, right? Right? And then the moment you put it into a computer, you index that by n already. Right? So this is n equals 0, 1, 2, 3, 4, etc. Right? If you want to map it back to the seconds, then you need to multiply by delta t. Right? So that's representation. Same, I'll come back to the frequency and later. Right? Frequency also, we say 1 Hz, 2 Hz, 3 Hz, right? So our delta k is 1 Hz. Right? But just now I asked you to compute. It's actually, in real life, it's actually 0.0 something Hz, understand? The delta k here. Okay? So just bear that in mind. And we know that signal can be sine, can be cosine, but in real life, signal is never pure sine and never pure cosine. Right? Right? Or frequencies that come into it here is most likely a combination of sine and cosine. That's a shift version, okay? Right? Now the good thing about it is, let's say 5 Hz, right? You have some sine of 5 Hz, you have a sine wave of 5 Hz, right? Right? And if you move it here, it becomes still a 5 Hz, right? You shift it, it's still a 5 Hz, right? Right? It's a bit of sine, a bit of cosine, right? But still 5 Hz. The good thing is, you can represent this shifted version by a summation of sine and cosine, understand? Yeah? Okay? If it is more like sine versus sine, then AK will be big, BK will be small. If it's more cosine, BK will be big, AK will be small, understand? Okay? And the comparison between AK and BK gives you the phase, like what Stan was saying. Okay? Okay? So, any signal, this is something I want you to just accept it for the time being. And this is what Fourier told us also. Any signal can be represented in this form. Okay? Any signal in the world, right? Any signal in the world can be represented in this form. So K is the total number of frequencies. In the demo that I gave you, 540,000 type of frequency. Okay? And you can represent a piece of symphony orchestra music well enough. And the coefficients AK and BK define the sound that you hear. This is one statement. This is a very, very important statement, understand? Right? Why is this so important? Because AK and BK tells you whether the particular frequency is there or not, yes? If it's 0 means it's not there, right? Now the relative strength of AK and BK, when you compare AK and BK, it will tell you, yes, the frequency is there and it is more sine or more cosine, right? Yes or no? Yeah? So this is a very important statement, although it's just like that. And the whole game about frequency analysis is to be able to find out what is the AK and BK for any signal that you're given, understand? And the way to do it is to do something called Fourier analysis. Okay? Okay, so assuming we are given the values of AK and BK, vary K from a small number to a large number. Okay, since I think I'll play. We break this. This is music again. Okay, so this is the music, right? Of 20,000 Hz, right? Divided into 524 frequencies. So every frequency component, the delta M is like 0.0 something, right? And then if I use a full if I add up all the frequencies together, this is what you hear. Okay? Now, listen up. Now we talk about the AK and DK, right? We have a low frequency with a high frequency, right? Okay? Now, if you do Fourier analysis, then you know all the AK and DK. After the analysis, which is what I did, right? I know all the AK and DK. Let me see. For 1 Hz, what is the A and B? For 2 Hz, what's the A and B? For 1.01 Hz, what's the A and B, right? Right? Now, I can play magic now. I can only play the high frequency components. I can only play the lower frequency components, right? Right? And if I play only the lowest 5000 frequency component, you practically don't hear much. You don't really hear much, right? Yeah, that's the lowest frequency. So you see the beauty of frequency analysis now? I can take the signal and I can play with it, right? And in fact, those of you who play with your audio gadget, right? You can actually do equalizer, you have the bass and things like that, right? It's all frequency, playing around with frequency, understand? And then if you just do the top 40 Hz, 40,000 components, you begin to hear the music. So you see now, and the 40,000 is not as nice as 524,000, right? 500,000 is very clear, right? But you can control it, right? And then you can immediately see the effect now. Let's say if I don't have enough money to save the full data, I want to cut down the storage space, right? Right, and still be able to know what music is it. Then you store the top 40,000 and throw away the higher frequency because it still can be heard. Understand? Okay? So once you do frequency analysis, then you find that you have a lot of applications now. Okay? Now, okay, so we go to the basis set, right? And then I think I can quickly go through this and because it's all that we talk about just now. Okay? Basis vector, all the V's are the vectors that I was using, right? The V's. And the C's are like the projection of the vectors, right? Okay? How much component of C's and V's? The word, you have to get used to the word span. Huh? Span means what's the other word for span? That means it can represent, it can occupy the entire space, understand? Okay, so the set of n by 1 vectors that can be used to represent all n by 1 vectors is called a basis vector set. Notice something, I use the word vector and function interchangeably, right? Right? Because sign is a function, right? By representing some function using a vector, right? Yeah? So I use it interchangeably. So basis vector. Okay, there's another thing that is not written here, but I want you to know it. This is known as a linear combination, right? Linear combination of the basis vectors B, and the coefficients for the linear combination is C. Understand? That means it tells you how many components of each of the basis functions are there. Okay, so basis very important. And you want orthogonal basis function, right? We explained just now why you want orthogonality. And why is it desired? I leave it to you to see some examples here. These are 3 examples to show you why is it convenient to use orthogonal basis functions. Okay? Now we know that in vector space, you have the notion of basis vectors, right? And we also know that choosing a set of basis vectors, it is most ideal if the vectors are orthogonal to each other, right? We all agree orthogonality is useful, right? Right? Imagine if the sine waves and cosine waves are not orthogonal to each other. You have a lot of problem, right? Right? And I tell you what is now because they're orthogonal to each other, I know that there will only be one vector that will respond, right? If I say sine 5 hertz, only sine 5 hertz will respond, right? So in analyzing the signals, we wish to describe the signals in terms of its basic signals. The challenge is, what should these basic signals be? We do know that ideally this set of basic signals should be orthogonal to each other, and as to what exactly should be these signals, it depends on what is the purpose of our analysis. Remember, if you want to represent space, right? Spatial information, X, Y, and Z, that's the best, right? If you want to represent frequency, you better rotate them in such a way that all the axes becomes sine waves and cosine waves, right? Okay? Then you actually tells you the frequency component. Okay? So in most applications, such as analyzing music, what we want to know is the frequency content of the piece of music that you are hearing. Right? Therefore, we want the basic signals to represent frequencies, and we also want these basic signals to be orthogonal to each other. And it is sine and cosine, right? So then we come to the Fourier series. And Fourier is like 200 years ago, yeah. 200 years ago. In fact, Fourier's, some of you may have heard of Laplace, right? Laplace is actually the teacher of Fourier. So Fourier proposed to represent the signals in terms of frequency, and it became the foundation of modern signal processing. Okay, and many other things. A lot of things you can use Fourier analysis, not just in signal processing. Alright? So he proposed the use of sinusoidal. Sinusoidal means sine and cosine. Okay? As a basis function. But sinusoidal signals are, okay, this is something that as we go through the slides, there are more and more inaccuracies that intentionally hidden from you just now. I don't want to confuse you, but we'll uncover slowly. Right? Now, just now I did say that any signal can be represented as a sum of sine waves and cosine waves. Yes or no? Yes, right? Now, sine waves and cosine waves are periodic signals, right? Right? So when you add up sine waves and cosine waves, when you add up sine waves and cosine waves, when you add up sine waves and cosine waves, when you add up sine waves and cosine waves, it must be periodic also, right? But do I speak like that in practice? No, right? No, right? Okay? We will address this next time. Okay, why we still can use periodic signals to represent signals that is obviously not periodic. Okay? But let's just take it from now, that we can do that. Right? So a linear combination of sinusoidal signals should intuitively be periodic as well, right? It's true, right? So are we limited to analyzing periodic signals only? Not quite. Right? But we will start off by analyzing periodic signals first, right? Then we see how to bring it to non-periodic signals. Right? Periodic signal is known as Fourier analysis. To deal with non-periodic signals and periodic signals in general is something called Fourier transform. Right? We'll do that next time. Right? But do periodic signal first. Right? Now, there's something very fundamental in the periodic signal. Periodic signal, you need to measure the period, right? The period T. The fundamental period is beyond which the signal repeats again, right? Yes? So the period is T, and there's a fundamental frequency called the T. 1 over the period is frequency, right? I think you learned this in your physics, right? Yes? Right? 1 over the period is frequency. The fundamental frequency, cycles per second or hertz, right? Hertz are the car rentals company hertz. What is sinusoid? Sinusoid is sine and cosine, and what defines a sinusoid is frequency, which is the F here, the amplitude, which is the A here, and phase, which is something here, right? So you can represent a shifted sine or a shifted cosine, understand? Right? You can write it in this form, or you can actually write it in another form, which is This one. This one. Right? A pure sine, unshifted sine, unshifted cosine, add them up together. Weighting A and AK and BK, right? You write it in this form, is equivalent to writing it in this form, understand? It's equivalent to writing it in this form. Okay? It's equivalent to writing it in this form, right? That means if you are too lazy to write the phase, right? You can don't write sine with a phase cosine. The phase, just say sine cosine add up together. Okay, both are equivalent. All right. Now, so the sine wave, everyone knows what is a sine wave. What is a sine wave or different this? Top one is a sine wave. The bottom one is a cosine wave, right? Right. The shape is the same. You just shifted by 90 degrees only. Right, and the magnitude is how wide it vibrates, right? And the phase is like the shift, right? When you add two sinusoids together, will the sum be periodic? This is something that when you add two periodic, when you do add two periodic waves together, right? Will the signal be periodic? Yes, yes, but why I say not always? Not always is when you start to use mathematics, understand? Okay, when you start to use mathematics to represent things, then you find that mathematics doesn't quite agree with your intuition. Okay, and the culprit is what? The culprit is something called irrational number, understand? It's pi irrational number. Pi is an irrational number, right? The culprit is pi. Okay. Because pi cannot be written as the division of two integers, right? Right, and that is a problem, right? For example, and okay, this slide and this slide, this slide and this slide, it's best that I leave it to you to go and digest rather than talk. Because the more I talk, I think I'll confuse you. Okay? So basically, what it means is, what I want to say is. When you add sine and cosine together, right? You see, we always write sine 2 pi st, cosine 2 pi st, right? When you have pi, you better stick to pi, understand? You don't go and add a sine 2 pi st plus sine 2t, you understand? They are not periodic now because pi is irrational number, understand? Okay? Okay? And if you don't have pi on both sides, it's fine. If you have pi on both sides, it's fine. You cannot mix them, right? You cannot mix them. For this case, when you don't have a pi for your sine, you have a pi for cosine, then it's not periodic. But when you have pi, then it's periodic, understand? Okay? Okay? But this is mathematical representation, right? Right? And in real life, you won't encounter this. This is just to make you be aware, right? When you write, because you can always write sine 2t, right? But make it a habit to use pi and be consistent from. Otherwise, you may run into problem, right? Okay. So I leave it to you and to figure out why is it GCD also. So these three sides I leave it to you. So are sine, cosine orthogonal functions? Yes or no? Yes, right? We said that just now, and this is a proof. Right? When you have sine and cosine, sine and sine of different frequencies multiplied together, you get some number. Actually, you get t over 2, right? But actually, I don't even care whether it is t over 2. I just want to know it's a big number or 0. Understand? Okay? So when n is equal to n, that means the frequencies are the same. When sine waves of two frequencies multiply with each other, it gives us 0. Now, can everyone see that this integration sign is the dot product? Can everyone see that? Multiply sign and another sign together and sum them up is what this integration is doing, right? In the continuous flow, right? Can you see that? Can you see that this integration sign is equivalent to dot product? You have to see this, a very, very critical point. Integration, you see you see you have the sign, right? You have the sign, right? You have another sign, right? You multiply them point by point, right? And then you integrate them means you sum them up, right? Right? Isn't this like in the discrete time law is like multiply and sum, right? Which is a dot product, right? Right? So I'm using dot product with integration interchangeably, understand? A lot of things I say here, if I go to maths department, the maths professors will shoot me, They'll beat me to death. Because I'm not being very exact here. Right? I'm not being exact here, but we don't have to be very exact. I think what we want is the concept. Okay? So when I say this is dot product, that's what I meant. Understand? It's almost equivalent to dot product, right? Yes or no? Yes? Okay, So you can prove that sign, when you multiply with sign, it gives you 0 or some and it gives you non-zero answers when the frequencies are the same. Can I have a show of hand? Is the lecture this morning too heavy? It's okay, Okay, good. And then when you have cosine, same thing, right? It will be 0 unless the frequencies are the same, understand? Yes? No. When you have sine, cosine, that's the best thing in the world. Sine and cosine will never see each other. They will never like each other, they will always be 0, understand? Even if they are the same frequency. And that's a good thing, isn't it? Right? Because that's a good thing, because that allows us to analyze, is this a sine, is it a cosine, and by comparing the relative strength, you know how much is sine, how much is cosine. So in summary, two sine functions, when you dot product, I say dot product you get 0, unless the frequencies are the same. When you have two cosine, dot product 0, unless the frequencies are the same. Sine cosine will always give you 0 even if they are the same frequency. Understand? Okay, very critical. Now, what about sine cosine with non-zero phase, right? As I say, non-zero phase you can always, trigonometry you learn, right? You can always break them out into pure unshifted sine and shifted cosine. Just this thing, right? Right? And the cosine phi and the sine phi corresponds to what AK and BK just now, right? Yes? The strength of sine and strength of cosine, right? And what did I tell you? You compare the relative strength of A and B, you know how much the shift is, right? Right? Okay? Okay? And this is what you can derive from here. In fact, you can get a meaning of the sine cosine. Sine cosine, if you do a ratio, right? You get a tangent kind of thing. So you can get the phi, angle phi, but that part you work out, you should be able to figure it out. I won't elaborate on that. Okay? So a sine that is shifted is equivalent to weighted sine or sine and cosine. So cosine that is shifted is also equivalent to weighted sine or sine and cosine also, right? So let's forget about this form. Let's just use sine unshifted and cosine unshifted, A and BK. Okay? So in general, the sum of sinusoidal signals, even with non-zero phase, can be written as a linear combination of sine and cosine with 0 phase, right? With 0 phase means unshifted. Okay? Now we'll see later that any signal can be represented as either this or this, right? Any signal, right? Right, we should say any periodic signal for the time being, any periodic signal. Okay? Now, so A is this and BK is this, and so any shifted sinusoidal waves can be represented as sine and cosine, and this will be the form that we want to use. Right? Okay? Okay, So any periodic signal is a linear combination of sine and cosines, right? There's a repeat. Given the signal, that's $1 million question, right? If I give you a piece of music, right? Find out how to find out what is AK and BK. We just did it just now in the first half of our lecture, right? All you need to do is just take the piece of music and dot product with all your basis functions, right? And you got all the AKs and DKs already, right? It's that simple, okay? It's that simple. So A is given by integrating over one complete period. Okay, integrating over one complete period is our dot product, right? And you must finish one complete period or multiples of the period, understand? You cannot do halfway. You're not saying, when I say the two vectors are orthogonal to each other, right? You cannot take half of the vector and half of the vector and dot product and still expect them to be zero. You cannot, you have to take the entire vector, understand? Yes? So you have to take you have to take the complete period, okay? And dk is given by integrating over one complete period. We did it this morning, right? We just did it this morning. So some simple integration, I think I can skip this. This is not a maths course, and I don't expect you to go to the exam. I'm not going to test you how to integrate things and things like that. It's not a maths course, and I don't like to do that also. And this is a computer science course, right? And computer science course, you are all very good in coding, right? Right? So no matter how complicated is the function to be integrated, let's do the numerical way, understand? And the numerical integration is what? Integration using adding up all the trapeziums, right? Yes? Right? So we are going to do that, understand, for this course. You are not going to do complicated maths, okay? I myself would like to do it, and it's not a maths course also, right? So let's do the area under the curve, right? If you integrate this curve, the area under the curve is the integration, right? Right? So you draw trapeziums and things like that, right? And the more trapeziums, the finer the trapezium, the more accurate is the answer. Okay? Now, as I mentioned, any signal, this is one example of a composite signal, right? I add a few sine waves and cosine waves, shoot them around, and then you get any kind of signal, right? Okay, and given a composite signal, how do you find out what are the sine and cosine components? We did it this morning, right? Just take the signal and then dot product with all the basis functions. That's it. Okay? So this is what exactly is trying to tell you. Do not worry too much about all these things. Okay, as I say, absolute value is not important. Okay? It's a relative that's more important. Right? And we can represent any cosine with a shifted sign and vice versa. Therefore, for a signal comprising a linear combination of sine and cosine, it does not matter whether it is shifted or not shifted, the signal can be written as this form, right? If it is not shifted, then this is the phase is zero, right? Right? So this is another way of saying the dot product thing, right? This slide is just another way of, it's just repeating what we said just now. There is something that I want to introduce now. See, you given a signal, right? You don't know if it's sine or cosine, or you don't know what kind of signal is it, right? Okay. Then I know that I have the 1,000. I use 1,000 is also, in actual fact, it's going to be a few hundred thousand. That's 1,000, right? 1,000 basis functions, right? And then you dot product with it, right? Then I say, Stefan and Sam, right? Or try to remember all your names, right? And Stefan says, how do I present the result, right? So the result that you present is, okay, you have strength 10 of sine 5 hertz, right? And strength 2 of cosine 5 hertz, right? So that's the answer, right? Right? But it's a very cumbersome way of saying things, right? Okay? So instead of saying that, we want to represent it using a mathematical object called complex number, understand? All of you have come across complex numbers, right? Real parts and imaginary parts. Okay? So the consensus is this, the dot product result with the cosine functions, right? We put it in the real part. The dot product result with the sine functions, you do it in the imaginary part, understand? With a minus, okay? Okay? And why is it minus? Convention, okay? Now, there is a very valid reason for doing this. There is a very valid reason for doing this. If you understand this, okay. If you don't understand this, don't think about it. It's not that critical, but listen. When you represent in complex numbers come with this actually set of mathematics that you can use. Understand? Complex numbers has got real part, imaginary part, right? Complex numbers has got the magnitude, right? Complex numbers has got the phase, right? And the magnitude and phase can directly be applicable here, understand? Right? We talk about how much the sine is shifted, how much cosine is shifted is a phase, right? So when you represent in complex number form, you can actually represent mathematically in a very elegant way, understand? You don't need to use English long-winded and explain things. Is that okay? Okay, and for complex numbers in our field, in engineering, in computer science, complex numbers, the imaginary number we represent as J, understand? You go to maths department, they use I, right? Imaginary number. We use J here because because I is the reserved word for electric current, right? So we use J here. Okay, so yeah. So you see all the complex number arithmetic here can give you all the phase. and the magnitude. There's one more thing before I release you. Exponential, a neater representation. See, now you have the signal that is given to me, right? Input signal. You multiply you dot product with cosine. The same signal, you dot product with sine, right? Yeah? Yeah? And then you combine the two and say, okay, dot product with cosine, put as real part, dot product with cosine is imaginary part, and then I put in this way, right? Okay? It's a very long equation, right? You can shorten it because there is this formula called Euler's formula. Euler's formula says that e to the power of j theta equal to cosine theta plus j sin theta. So from here, you can actually write it in this form. And this is the neater form. So listen, this is the input signal, right? And you dot product with e to the minus j to minus kt. It will give you the frequency components that you're looking for. Understand? Okay or not? Yeah? And congratulations, you just learned Fourier series, understand? That's what Fourier series is about. Okay? And remember, you have to integrate from 0 to t, right? Right? And that's the end of this set of Fourier series. Next week, we are going to learn, because remember, your sine, cosine, add up sine, cosine, they'll give you periodic also, right? You give you periodic also, I don't talk like that, right? I don't talk like that, right? I don't talk periodically, right? Right? But how to use this kind of analysis when you require a signal to be periodic to analyze the non-periodic signal. Next week we'll talk about it. But just to give you some preview first, huh? We are going to play cheat, understand? We're going to play cheat. We're going to say, give me a signal. This signal is not periodic, but it is periodic. It will repeat again at time infinity. You're going to say that it is periodic, but the period is infinity, understand? Okay? You're going to assume that. And that kind of assumption brings you to Fourier transform, which is the same as Fourier series. It's just that you extend the period, because it's not periodic, so you extend it to infinity, minus infinity plus infinity in time. And then claim that it is periodic, understand? Because after infinity, nobody knows what's happening, right? So you claim that it's periodic, okay? And then you still use the same mathematics, understand? Is that okay? Thank you very much, and see you next week. Thank you. And I'll give you the